All right, in this video, we're going to be looking at an intro to our next unit, which is on vectors. So, vectors would help us answer a problem like this. Imagine you have a boat, it's traveling east, and it's windy. We want to be able to answer a question about how the wind is going to affect the boat's path. So, we could be thinking about what kind of information do we need to know to answer this question? And throughout the unit, we'll be looking at ways to model a problem like this and see what kind of impact the wind is going to have on the boat. So, the definition of a vector is this: it's a mathematical representation with both a magnitude and direction. And magnitude just means it has a size. So, certain things, certain quantities, are only determined by their magnitude. Things you've looked at like length and mass and temperature and energy. You've looked at these obviously in science. So other things require two numbers, both magnitude, again, which is size, and direction. Things like velocity, acceleration, force, and other things in science. And all of these are vectors, so when they have both a magnitude and a direction. So here's another list of the differences between scalars, which just have magnitude, and vectors, which have both magnitude and direction. So the way that we model vectors is with an arrow that has a tail, the starting point, and the head, which has an arrow, and the arrow shows what direction it's heading in. The length of the arrow shows the magnitude. So again, here's kind of a way to conceptualize why these are helpful to us. If we have a plane headed, let's say due north, this vector represents the direction it's headed as well as, in this case, it would be the speed. The magnitude would be like the speed. And then the wind is coming from this direction and it has a much smaller magnitude. So obviously, the wind is going to affect the path of the airplane. And if we add these two vectors together, which we'll be looking at shortly, we can determine both the magnitude and the direction that the airplane will actually go based on the wind. And that's represented in this picture right here. So in this first video, we're going to be looking at this note sheet. The first part of the note sheet, we're going to be defining the vectors, looking at different notations, and then we're going to start graphing. So you want to have this note sheet because I'm going to go through all of these examples in this video. So as far as graphing and notation goes, vectors, there's two main ways to show the notation of a vector. One is called component form, and that uses these pointy brackets, and the other is called the IJ form, and both of them break the vector into horizontal and vertical components. Okay, so how far it's going in the horizontal direction, so we can think about that on the x-axis on a coordinate grid, and then the vertical component we can think of the distance on the y-axis. And because we're so used to the coordinate grid going x and then y, vectors use the same notation. Horizontal you can think of as the x, and vertical you can think of as the y, and it goes in that order. All right, so just to kind of recap what I have already discussed, a vector is a mathematical representation with both a magnitude, which again, kind of helpful to remind us that that just means size, and it has a direction. Both of those things are equally important with a vector. You need to know both of them. And like that last slide showed, there are a couple of ways to notate, have a notation for vectors. So if I'm looking at this vector, vectors are typically labeled with a lowercase letter. And we have this vector in the coordinate grid, right? And I can see that if we start here, this is the starting point, it's the tail, this is the end because it has the arrow. The horizontal component is 1, 2, 3, and the vertical component is 1, 2. So in the component form, we have 3 for the horizontal component and 2 for the vertical component. And then in the ij form, we have 3I, so this just stands for the horizontal component, plus 2j. We're going in the positive vertical direction, the positive horizontal direction, and the positive vertical direction. All right, now as far as magnitude goes, we want to know the length of this vector because that represents the magnitude or the size. So if we think about this, we can use the Pythagorean theorem to find the magnitude because I know that this is 3 and I know that this is 2. So then I can just use a squared plus b squared is equal to c squared. So the length of vector u, the magnitude, is going to be 3 squared plus 2 squared, a squared plus b squared, and then the square root of that. So we have 9 plus 4, which is 13. So the magnitude is the square root of 13. And the way that we notate that is we say that that is the magnitude, just like the absolute value symbol is what's used, of u. Now, depending on the context, you might decide to leave it in radical form if it's an irrational number, or it might be helpful to find a decimal approximation. All right, so as far as the direction goes, we are going to be thinking about direction in terms of an angle. The way kind of I think about this is if we wanted to know, like if this was an airplane traveling, we want to know what direction it's going, what angle it's going at. And we've really been in the mindset of radians, but with vectors, we're actually going to go back to degrees because with so many application type problems, it's just more familiar and useful to be looking at angles in terms of degrees. So if I want to find the direction, I am looking for this angle right here, okay? So to find that, I'm thinking about that. I want to find this angle, and I know the original information gave me the opposite and the adjacent. Well, opposite and adjacent deal with the tangent ratio. So I can set up an equation. The tangent of theta is equal to 2/3. And this relates exactly to our last unit where to find the angle, we're just going to find tan inverse. So tangent inverse of 2/3 is going to equal theta. And for this, I need to use a calculator. And I want to make sure that my calculator is set in degrees for this unit. And I already did that, and I got 33.7, approximately 34 degrees. And if it doesn't say what to round to, just use your judgment on that. But I'm going to say approximately 34 degrees. Now, something that we'll see in some upcoming videos is that our calculator is just going to give us the reference angle. So we're going to have to be mindful of what quadrant we're in, but we'll look at that. We'll look at that eventually. Okay, moving on, we are going to look at, well, actually, I forgot about this. Something to keep in mind is that vectors do not have a fixed location in space. They are purely determined by magnitude and direction, okay? So think about this. If I have a vector with a horizontal component of 3 and a vertical component of 2, that is, all 3 of these vectors are identical. And I can move them anywhere I want on the coordinate grid, and they are going in the same direction. Like if these were airplanes flying, they are going in the same direction at the same speed, at the same magnitude. Their velocity is the same. So keep that in mind. Often we graph them at the origin on the coordinate plane just because it makes things a little bit nicer to work with. But if I had my vector up here, I could obviously, just like in the last example, make my right triangle and Pythagorean theorem still the same and tangent still the same, tan inverse. So just keep that in mind. Vectors do not have a fixed location in space. Okay, so now we're going to move on to graphing and notation. So there are 5 examples that we're going to look at, and we'll go pretty quickly through these because it's honestly pretty intuitive. Okay, so example 1. If we have a vector, it might tell you a starting location and an ending location. So for this particular example, we have a starting location at the origin, and we have an ending location at 4, -3. So if I draw that in, remember the ending location, like the arrow has to point at that ending location. All right, so there's my graph. And it says it's vector u, so I'm going to label it with a u. And then just keep in mind, so I would write this down as well. We can, like this is the graph of it, but if we want to write what, like represent what the vector is in a notation, we can say that this is vector 4, -3, because it goes 4 in the horizontal in the positive direction, and then -3 in the vertical direction. Or we can say 4i, and then since it's negative, we'll just do -3j. Either of these would represent this vector. And then, like we just talked about, we could move this anywhere on the coordinate grid, and it's still going to be 4 in the positive horizontal direction and -3 in the vertical direction. All right, example 2. It might, this one again gives us 2 points, PQ. Now it doesn't say where it starts, so if it doesn't say that, the assumption is the first point is the starting point. So we have point 2, 1, and we end at -1, 4. So there is our vector starting here and ending here. And on this one, you could, to find the horizontal and vertical components, you could count the grid. So I'm going 1, 2, 3, -3 in the horizontal, and 1, 2, 3, +3 in the vertical. So that would be right the same as -3i plus 3j. Or you can be thinking, hey, from 2 to -1, that's a decrease of 3. So -3, -1 minus 2, you could go that way. 1 to 4, that's an increase of 3. 4 minus 1 is 3. You just have to have a way to do that. All right, moving on to example 3. This one gives us the component notation. And we have, I think I forgot on this one, vector v. You should label that on the graph. Okay, so back to this one. Vector v, it gives us the component notation. Now you could start anywhere on the grid. I'm going to go ahead and start at the origin, and it says -4 in the horizontal direction and +2 in the vertical direction. So boom, there is my vector. Again, just making sure that the arrow points at the last point, the head of the vector. Okay, this tells us what direction we're headed in. And again, if I wanted to, I could have started here, for instance, and gone -4, 2, 3, 4 in the horizontal direction and 2 in the vertical, and this vector would be exactly the same. And then I can label those as V. You only need to graph one of them. But again, I'm just trying to emphasize that point that these vectors are the same. It doesn't matter where they are in the coordinate grid. All right, example 4. This one is given in IJ notation. I'm just going to start at the origin, and it says -3. That's the horizontal component, so 1, 2, 3. And -2 or -2 in the vertical direction, so I count 2 down, and I have my vector. That's a little bit off, but you get the idea. Right there, and that is vector u. So there we go. And if I wanted to write it in component form, that'd be -3, -2 with those pointy brackets. I'm sure they have a name that is more, correct, but I'm just going to call those pointy brackets. And the last example. This one is giving us the magnitude. Okay, that's what this symbol means. It's saying the magnitude of V is 6, and it gives us our direction. Our theta is 110. So when you have a problem like this, you can just eyeball it on the grid. So the first thing I guess I would do is I would eyeball where 110 degrees is. And we're going to, for any of these, like with the angle, you want to be thinking about standard position. So I'm going to start at the origin. It makes it easier for me. I know that this is 90 degrees, and I know that like here would be what, 120. So 110 is obviously just a little bit past 90. So that is where I'm going to draw that in. And then it has a magnitude of 6. So, you could be more accurate by using the Pythagorean theorem, but I'm just going to estimate that I would say that 6 would be about here. And then what you want to do to convey the information from the problem is that we're going to like draw this in as 110 degrees, and I'm going to label this as 6, and I could also put a V there. That kind of, it shows like, hey, we have a magnitude of 6 on vector V, and this is 110 degrees. And again, if we wanted to, we could move this, but it just made life a little bit easier to start at the origin. Okay, that's graphing. Again, pretty darn intuitive. The next video is going to be talking more in depth about finding the magnitude and direction.